Your app goes viral. 50,000 users hit it at once. One server. It slows down. Then it crashes. Every single user sees an error. That's not bad luck. That's a design problem. One server means one point of failure. It crashes, your app is down. You deploy an update, your app is down. Traffic spikes, your app is down. The fix is simple. Run multiple servers. Put a load balancer in front. Traffic comes in, the load balancer spreads it across all your servers. One server fails, load balancer removes it. The rest keep going. By the end of this video, you'll understand exactly how Azure Load Balancer works. You'll know how to set it up. How to keep your app online no matter what. Let's get into it. Azure Load Balancer works at layer 4. That means TCP and UDP traffic IP addresses and ports. It doesn't read your HTTP headers. It doesn't know your URLs. It just sees packets and decides which server gets them. Now, here's something most people miss. There are two SKUs. Basic and Standard. And choosing wrong costs you. Basic is old. Limited features. No zone redundancy. Microsoft is actually retiring it. Don't use it. Standard is what you want. Zone redundant. Secure by default. Scales to millions of requests per second. Think of it this way. Basic is a toy. Standard is the real thing. Always deploy standard. No exceptions. This is where most people get confused. So pay attention, this one matters. Azure Load Balancer comes in two types. Public and internal. A public load balancer has a real public IP. External users hit that IP. The load balancer routes them to your backend servers. Use this for anything facing the internet. An internal load balancer has a private IP. Only reachable from inside your virtual network. No public exposure at all. But here's where it gets really interesting. Most production systems use both. Web servers behind a public load balancer. App servers behind an internal load balancer. Database cluster behind another internal load balancer. 3 tiers. 2 load balancers. And only your web tier is ever exposed to the internet. That's proper architecture. The backend pool is your list of servers. Simple as that. You add VMs to it. The load balancer distributes traffic across them. You can add individual VMs or a VM scale set. Use a scale set for production. Why? Because when the scale set adds a new VM, it joins the backend pool automatically. No manual steps. No missed servers. Now, this is the part most people skip. When you need to remove a server for maintenance, don't just yank it out. Use connection draining first. It tells the load balancer, stop sending new traffic to this server. But let existing connections finish. Without draining, in-flight requests get cut off. Users see errors. With draining, everything completes cleanly. 30 seconds of patience. That's all it takes. Health probes are the most important part of load balancing. And most people barely think about them. Here's how they work. Every few seconds, Azure sends a small check to each backend server. Server responds correctly, it's healthy. Traffic flows. Server stops responding, probe fails. After a few failures, Azure marks it unhealthy. Boom. Removed from rotation. No traffic goes there. But here's the mistake I see constantly. Developers configure a TCP probe on port 80. A TCP probe only checks if the port is open. It does not check if your application is working. Your server could be accepting TCP connections, while your app is completely broken inside. Use an HTTP probe. Point it at a real health endpoint. One that checks your database. Checks your cache. Returns 200 only when everything is genuinely healthy. That's a real health check, not a fake one. A load balancing rule connects the dots. You define a frontend, the IP and port your users connect to. You define a backend, the server pool and port they listen on. The rule links them. Example: users hit your public IP on port 443. Your rule maps that to your backend servers on port 8080. Done. But here's where it gets interesting. How does Azure actually pick which server gets each connection? It uses a 5-tuple hash. Source IP, source port, destination IP, destination port, protocol. Hash the 5 values, get a number, that number maps to a server. Same 5-tuple always goes to the same server. And the really useful part? You can define multiple rules on one load balancer. Port 80 goes to one backend pool. Port 443 goes to another. One load balancer. Multiple applications. One public IP. Here's a scenario that breaks apps in weird ways. User logs in. Their session gets saved on server A. Next request. Load balancer sends them to server B. Server B has no session. User is suddenly logged out. For no reason. This is the sticky session problem. And it happens more than you think. If your app stores state in server memory sessions, shopping carts, file uploads, you need client IP affinity. Same user. Same server. Every time. But, and this is important, affinity is a bandage, not a fix. If that server crashes, all those sessions are gone anyway. The real solution? Make your app stateless. Store sessions in Redis or a database, not server memory. Then you don't need affinity at all. Any server handles any request. Your app scales cleanly. No fragility. Use affinity as a short-term fix while you re-architect. This one trips up almost every developer deploying Azure Load Balancer for the first time. I'm not exaggerating. Your backend VMs need outbound internet access to call external APIs, download packages, send telemetry. But they have no public IP of their own. So how do they get out? Through SNAT, Source Network Address Translation. The load balancer translates their private IP to a public IP for outbound traffic. Sounds simple. Here's the catch. Each public IP gives you roughly 64,000 SNAT ports. Each outbound connection uses one port. Your VMs make hundreds of simultaneous connections, those ports fill up. New connections start failing. Your app breaks in mysterious, hard-to-diagnose ways. The fix? Add more public IPs to your outbound rule. Or better, use Azure NAT Gateway. It's built specifically for high-volume outbound traffic. More ports. Better performance. Cleaner solution. Let's talk about what real high availability actually looks like. An Azure region has multiple availability zones. Think of them as separate data centers in the same city. Independent power. Independent cooling. Independent networking. One zone has a power outage, the others don't even notice. A zone redundant standard load balancer survives a full zone failure automatically. No manual failover. No intervention. It just works. But here's the catch most people miss. The load balancer surviving doesn't help if your servers are all in one zone. Spread your VMs across Zone 1, Zone 2, and Zone 3. Zone 1 goes down, health probes detect those VMs as unreachable. Traffic automatically redirects to the healthy zones. Visual idea: 3 zones, VMs in each, 1 zone fails, traffic arrows redirect. This is your baseline for production. Zone redundant load balancer plus VMs spread across zones. That's the 99.99% SLA. That's real high availability. Setting up monitoring takes 5 minutes. Skipping it takes hours to debug when something breaks. For metrics you must watch. Data path availability: is the load balancer itself working? This should always be 100%. If it drops, something is seriously wrong. Health probe status: what percentage of your backend servers are healthy? Alert the moment this drops below 100%. That means a server just went down. You want to know before your users do. SNAT connection count: your early warning for port exhaustion. Watch the trend. If it's climbing, act before it becomes a crisis. Byte count: your traffic volume. Useful for capacity planning. Set those alerts today, not after the first incident. And that wraps up Azure Load Balancer. You now understand why it exists, how it works, and how to use it right. Health probes. Backend pools. Zone redundancy. SNAT. All of it. This is part 17 of the Azure series. If you're serious about becoming a cloud engineer, subscribe and keep going. Next up, Azure Application Gateway Layer 7 load balancing with SSL and WAF protection. Don't miss it. Let's think through this step by step. The VM is running, so it hasn't crashed. The config hasn't changed, no one removed it from the pool. But traffic completely stopped going to it. What's the most likely cause? The health probe is failing. The VM is running, but your application on that VM is not passing its health check. Maybe the web server process crashed. Maybe the app is throwing 500 errors. Maybe the database connection is gone and the health endpoint is timing out. Here's the key insight. The load balancer doesn't care if the VM is powered on. It only cares if the health probe succeeds. A running VM with a failing probe gets 0 traffic. To diagnose this, check the health probe status metric in Azure Monitor. Then SSH into the VM and check, is the app process running? Curl the health endpoint directly. What does it return? Active recall: health probe status determines traffic, not VM power state.